Oh, hey guys.
Yeah.
So let me share my screen. So that's that one. Let me know if you can see my screen.
Yeah, I can.
Yeah.
Okay, cool. Yeah, so I must confess I didn't know some of the techniques in this chapter. So probably you guys know more about it than I do. But was there anything in particular that kind of really leapt out at anybody before I just sort of go through my little notes here?
I just felt this was one where going through the code would be, it's like totally essential. So just to get a good feel for how this works.
Yeah.
Yeah, there's some nice plots, particularly with the confusion matrix, because I hadn't come across it before. I had to read it twice just to get an idea of what it was.
Yeah, I found like the precision and the TP and the FP like kind of confusing. There was a bit of jargon that I hadn't come across before.
Yeah, so I had to go back to this diagram here to just kind of even get an idea of what he was talking about, because I found it really confusing as to what these two meant and why. I still don't think I've got it fully. Let me actually put that to this side.
Yeah, I think I understand like the terms, because I think I've heard it before, but yeah, it was the specificity and precision and recall, and I thought it was quite interesting that he made, like he kind of gave, just in the section about precision and recall, he did give like, like one is like how many times it gets correct and how many of the correct, the other one is like how many of the correct one it detects, which was quite an intuitive understanding. But yeah, I think I still need to like get a bit more familiar for it to be ingrained in my head.
Yeah, I know, I understand what you mean. I mean, I know what these things mean now. Precision is this guy here. So this is the true positives divided by the true positives plus the false positives. And the idea is that the more false positives there are, the lower the precision will become. Assuming whatever true positives was what it is. So that's kind of how accurate it was in predicting fives and not having as many false positives. But then the recall was this row here, which is the true positives divided by true positives divided by true positive plus false negatives, which was the more false negatives you do, the lower the recall becomes. So the highest recall you could get would be 1, which is that all were true positives. There were no false negatives. Okay. But I haven't got like a good intuitive feel for it yet. I can understand what the formula is saying, but until you see some numbers and some graphs, I guess it's hard to get a really.
And I think the famous example with respect to these true positive or precision and recall is they give what and why do you care about which one, like precision or recall. And most of the time they give example about the cancer detection. So what they say is that time around you are looking for more on true positives. Hang on a second. So you want to avoid the false, I think false negative, which you want to avoid on all cost. In a sense, you don't want to, in general, you don't want to let anything telling that you don't have a cancer and they have a cancer, that sort of stuff. So I think that's one of the examples they generally use. So what you care about, and then you just walk back and see, oh, that's the recall, which we want to minimize it, so on and so forth.
Oh, yes. Oh, interesting. Yes.
Good example. Yeah.
So they gave the example of like children's videos, didn't they? Where you didn't want any kind of naughty videos to go through. So that if the classifier was giving any false negatives, then really that would have to go through an actual person.
Yeah.
And I guess precision would be that it wasn't giving any false positives. So if somebody was, yeah, I don't know what kind of situation. I guess a cancer or something, you know, you don't want to give a false positive to a person. Could be life-changing for them. So yeah.
No, but then in this case, you could, in terms of a cancer, you're allowed to have a false positive. In a sense, that's not that decremental. Obviously, there are like other issues. However, you focus more on the people. You don't want to tell people that you don't have it, slip under the radar. You want to catch all of them. Even though during your test, you are letting those false positive coming in, that's fine. But the false negative, which you care about. So that's why, and again, like as he mentioned, between precision and recall, whether you want to be your algorithm to be a very, very precise, whether you're looking for the precision of the algorithm or whether you're looking to minimize the recall, so on and so forth. So again, as he's explaining that you can't have both of them. So there is always a trade-off between the two.
And then they had this harmonic mean, which was like a combination of the two, which you could, where you want like the best of both worlds, but you want to find that middle ground. Where I didn't fully understand this equation, but they've got some graphs in there, haven't they? So there was precision recall. So this was precision versus recall. So you can see one is kind of the opposite of the other, but they're not like exact mirrors. One is slightly more smoother than the other one, he was saying, and there was an explanation which I didn't really fully understand as to why one behavior.
So I didn't get what he was saying. It's a bumpy on some side. Do you have any idea where he said it's a bumpy? Is it this blue line on the top right corner? Is that what he means?
Yeah, I have to look for it.
Okay. It's not very bumpy, but it is bumpy.
Yeah.
Well, I guess it's down here there, isn't it? There's a, I don't know, maybe it's just my monitor.
No, I tried to find, and I thought maybe this, or maybe I gave up. So what he meant by this, when he says your precision is quite bumpy on a high, on the high threshold, any idea why?
Where's that here? The reason is.
Yeah, so he does mention here, so how do you decide? And then, so you may wonder why, oh, here we go. You may wonder why the precision curve is bumpier than the recall. Let's have a look. So the precision curve he's saying is bumpier than the recall curve. The reason is that precision may sometimes go down when you raise the threshold, although in general it will go up. To understand what, look back at figure 3 and notice that what happens when you start from the central threshold and move it just one digit to the right. Precision goes from 4/5 to 3/4. On the other hand, recall can only go down when the threshold is increased, which explains why its curve looks smooth. Yeah, I'm afraid I still don't really fully understand.
So I get the point where he said the precision go from 80% to less, because the one before the one I think if you go back.
To figure 3.3.
Yeah, this one. So this explains that when we have a threshold on a point, I think in the middle, you have 4 5s out of 6, which are kind of like a true positive. But when you move that arrow to threshold to high, you are only able to recognize 3 out of 6. So precision goes down. So I got that point, but I still don't understand what does he mean by bumpy.
It just means like it's not as right. So like it's not constantly going up or staying flat. So if you like look at the top right of figure 3.4, you can kind of see almost just before like threshold is 40,000, it kind of goes down a little bit, whereas like you kind of either you want like your graph to stay flat or be increasing all the time, right? So like that's.
Okay, so it depends upon how your values are spread across. So you may have quite a lot of values between the thresholds, and which can make it either accuracy goes up or down based on your value threshold, which spread across, I guess.
I guess I wonder if he means, well, if the threshold was here, and we move it to a little bit here, then the precision will have gone down a little bit because we will have missed those two. But if we move it a little bit further up, then it'll stay flat for a little bit because the 6 was never really isn't really a positive result. And then if we go a bit further up, then the precision will start to
stabilize.
Yeah, stabilize. So there's like a little bumpy bit there. I don't know if that's quite right though. That was my.
No, I think you're right. Yeah, I mean, I think we said earlier the precision goes down. It doesn't. It actually goes up when you move the threshold to the right. Right.
Yeah, precision goes up as you.
Yeah.
In general.
Right. So I guess there's more 5s on this side than there are over there.
Yeah, you've got a smaller bucket. Yeah.
Okay. And precision is total positives over total plus false positives. Yeah, I guess. I mean, of course that makes sense because if you're here and that was one false positive, you can never have more false positives on this side than you had before. You only had whatever it was. The only thing that might happen is that you have now less false positives on this side as you move the threshold further up. So yes, that would make the precision go up. I think. Yeah. So and then he had precision versus recall. So this is a graph of the two. So at around the 80% recall, precision really starts to fall off. You will probably want to select a precision recall trade-off just before that drop. For example, at around 60%. Oh, okay. I guess if you plot these two, then you can get like an idea of what the best would be before it. Well, not best, but like what would suit you, I guess, in terms of your precision versus recall needs. And then
I wasn't really sure why he picked 60%, to be honest. I was like, you could just as easily pick 80%. I don't know.
Yeah.
I wasn't really sure why 60%.
I think it's totally arbitrary, which is why at the next sentence he said that the choice depends on your project. So
yeah, so it starts to really fall off here, which is over 80%. Maybe this particular threshold is just shown as a point of reference, I guess.
So one of the point he made was that we want to have this graph in the fall. We want to have most of the area under the curve. So that fall at 80%, we want to have this stretch to top right corner. That's what he mentioned in one of the point. We're going to cover the ROC curve, which is just the opposite of it. But this is what he was explaining, that you want to have this curve going from the top and slowly going flat all the way. If you can, it won't obviously, but that's usually what we try to do through the algorithm.
Right.
Okay.
And then we have the ROC curve. It is very similar to the precision, but instead of plotting precision versus ROC curve plots true positive rate, another name for recall, against false positive rate. The negatives that are incorrect plus false positives. It is equal to 1 minus the true negative rate. Yeah, again, hard to visualize. Let's look at one of these curves. Okay. So he said the ROC plots the false positive rate against the true positive rate. The red circle highlights the chosen ratio at 43.68% recall. I must confess I'm a bit lost on this one. I didn't fully understand what ROC really was doing. He mentioned something about the perfect classifier how ROC AUC equal to 1. Yeah, I don't know. Did anybody get what this curve is about and what it's showing?
Not entirely. I was a bit confused as well by this one.
Yeah, I think we need to read up more.
Yeah.
Yeah, I'm not. Yeah.
I have to go run the code.
Yeah.
All the acronyms don't help either.
Yeah, we definitely want to read a bit more about this AUC curve, because this AUC curve quite often comes in a deep learning or a machine learning on a various aspect. So we probably want to get the good hang of it. All I know is that he said that whenever we look for an AOC value, we are just looking for a value for which is close to 1. So that's area under the curve need to be maximized. And again, what he mentioned in one of the point, that what we want to do is this curve need to be stretched towards the top left corner. That's exactly we are looking that as much area we can cover under it, which is like ideal case. And again, going back to the point that this is the trade-off between precision and recall. So what we want both to be good. Obviously, they can't be because they are opposite. But that's how they are saying when we plot it, we try to get as much as area under this curve, and then once we have it, that means our model is good enough or quite good as such. That's the summary which I get from the AAC ROC curve.
Yeah, he's got another one, hasn't he, where he's actually done something, and here it's really pulled up towards the top left. Obviously, this is the one he's saying is going to be better.
Yeah, so that's the true classifier I think he has.
Yeah, random forest classifier.
Yeah, SPD random forest. Yeah.
And I think, and then there's various different types of multiple class classification. It's interesting because in neural networks, we normally use them as one hot encodings and then read off which one. But here he's got this notion of in scikit-learn, they've got various different ways of actually doing multiclass. They've got how they compare one model against another, one model against all the others, one model against another one, and the code seems to be able to do all of that under the under the radar for you, or you can explicitly select it. I think I got a kind of like a generic idea of what he was doing, but I didn't fully understand as to why we needed to compare individual classifiers. I guess maybe this is carrying on from the original one, which was 5 and not 5, which was 1 versus all, I guess, or 1 versus the rest.
The 1 versus, yeah, that's right. Yeah.
And then doing 1 versus 1 would be classifying 1 versus 2, 1 versus 3, and then and they said there was 45 of those you needed if you were going to do every single combination of them, and then take the best one. Kind of just understand it at a high level, but I don't really understand how it works actually, as to how do you choose like the best one.
Yeah, it was. I also I wasn't sure if you had two numbers that had one equal amount of duals, because he calls them duals for the 1 versus 1 strategy, and I wasn't sure how it would handle.
I think you'll have a decision boundary, so like a threshold, and you just choose normally which one to go on which side.
Oh, okay.
The decision boundaries are used. That's how they're used.
Yeah, it's interesting that they had support for using individual support vector machines to do the individual one, and it all kind of built it internally and did all 45 of them and gave the results. I was like, wow, that's interesting. It's doing a whole lot of work.
Yeah, that was new to me. I didn't actually get to the next section, so I just stopped at the end of this one. Or after error analysis, I don't know what else they've got in scikit-learn, if they actually just have the normal multi-class.
Yeah, so this one, this was this the multi-class. So this is multi-class, and this is where the sport vector machine stuff comes in. And it was all to do with sport vector machines can't handle a lot of data, and this would be one way of training it, where you create small sport vector machines. And then multi-class, so there was error analysis. That was the this is the confusion matrix.
Okay.
Multi-class, multi-label classification. And this was interesting, where they were doing individual pixels of it.
Yeah, I definitely didn't get this far.
Yeah, no, me too.
Oh, mind you, that was multi-output. Sorry, I'm confusing. I mean, this whole chapter is given quite a few different models, which I'd never really even considered before. So, yeah, so this is multi-label. So you've got something which can output three, true or false for three different things, like Alice, Bob, and Charlie, as to whether they're in the same picture. So it'll give you whether Alice is in the picture, Bob's in the picture, and Charlie's in the picture. So that's multi-label classification. That seems to be using k-neighbors classifier. Interesting how.
I guess he's just like throwing a lot of classifiers at us, really. So I'm not, I don't know. I'm not sure if anyone knows to say like that we can't apply the other ones here.
And then multi-output. Yeah, this is the one where you could have one class, but then have many outputs within that class. And this is where he's got the image and then the pixels within the image. And each individual pixels is 256 colors. Well, up to, what is it, like a grayscale value? And what was it he used to? So he's got some random hints. So he's doing K and N again.
Oh, okay, right.
And then that was the end. It looks like this is one which is might be worth doing all the code for, because just reading it, I don't really get like a good intuition for it. So I guess I don't know if it's worth doing that. We were going to do something practical anyway. Yeah, what do people think? Shall we just do this Jupyter notebook, or is there something else people want to play with instead?
We've still got like at least a bit more time, right? So we could like get started on the notebook.
Yeah.
Yeah.
Let's have a look to see if I can go to GitHub.
Yeah, I'll have to.
Non-ML. And GitHub. So there's this one. We run. And it is classification. Okay, and then I think I've got to call that built in here. I remember doing something with it. Where is it? Have I got call installed? Yeah, there we go. Okay. So this is just some system, scikit-learn, checking the version number, numpy and oz, random numbers, matplotlib, some basic project root. I'll run anyway. Don't know if it's running or not. Okay. Who's taking his time downloading that file? Okay, that came. Yep, so 70,000, shape of that is 70. Oh, that's just printing out 28 by 28. So this is going to show it. Okay, shown a 5. Let's say 5. Converting it to integers, and then function to plot digits. So, and then we're just showing some digits. Okay, so that's doing that. Creating the data sets. Okay, binary classifier. Right, so this is selecting the training and test sets of 5. So this is the stochastic gradient descent. The maximum trace is 1,000. Don't know what TOL is. Learning rate maybe. Random state 42. Fit. I must confess I didn't enable GPU on this, so I wonder if it'll be slow.
I'm not sure if GPU get used by default, or is it?
No, I remember you have to select a runtime.
No,
So,
but even if you
hardware acceleration GPU.
Oh, it'll restart it. Just you have to start again, and I don't think you'll need it. I don't think it'll help.
Yeah, it's not that big data set, so it should be all right. I run it on a CPU before on my machine, and it's not too bad. So
yeah.
So cross-validation score. So this is cross-validation score. So it takes input, the stochastic gradient descent, the training, the actual values for the training, and 3 folds. So this was the multi-fold.
Yeah, it mentioned something about the shuffling, didn't it?
You mean as a footnote?
Which was the
trying to remember where that.
Shuffling, did you say?
Yeah. Said it does do the stratified splitting and shuffling and all that for you.
Yeah.
It's already it's already shuffled. Okay. And I guess split for us.
Yeah.
So split. Yeah.
So in this case, the accuracy was around 96%, between 95 and 96% with the 3 different runs that it did. So far, I think none of this is like new, is it, guys? Or is there anything? I mean, I still don't fully understand what the cross-validation score is actually doing. I've got like an idea about it. He said basically it splits the data into 3 segments, trains on 2, and then validates against the 3rd. And then kind of does the same thing sort of 3 times because it's split into 3. And then I guess this is the accuracy each time.
I thought it's, what does it do is it divide your data into test and train and test set, and then CV3 it does 3 times. So every time it shuffle the data, create, train and test, and then run your model, and then do it again 3 times. So. Okay. I'm not sure, you can correct me if I'm wrong. I don't think it divides the data into 3 different sets and then run the program or algorithm. I think it run 3 times, but on the same data, shuffling it and then creating tests.
Yeah, again, I might be wrong as well, but I thought what he said was that when you set it to 3, it creates 3 folds. So it splits the data into 3, and then it says, each time I'm going to train it on 2 of those and test it against the 3rd one. And because we've done 3, you're going to get obviously, there'll be 3 combinations in there. It'll be the first one against the second 2, the middle one against the other 2, or the third one against the first 2. Is that all of them? I don't think.
Yeah, I think it's not dividing the data, but rather shuffling the data into 3 different sets.
Okay.
Yeah.
I might have to look it up. As I said, my understanding was slightly different, but you guys might be right. Sure. Oh, actually, there's a little description of it. A real life option default none.
No, I don't think it is shuffling the data. I think it's what Arshad said, because, well, that part is mostly done in the exercise for chapter 2. So there are a lot of cross-validation and grid search and all that. And yeah, so for cross-validations, from what I understand, is so, well, usually we have 5 or 10-fold. And then, for example, if we have 5-fold of data, so you train your model in the first 4-fold, and then you validate it with on the 5th fold of the data. So the purpose of the cross validation is mostly to tune your hyperparameters, and then afterwards, yeah, you can use it on your test set. But it's not shuffling. It's really dividing your data into a smaller training and test set. But it's not for the performance of your model, but only for the tuning of parameters.
Yeah. For next week, I'll try and look up what exactly this CrossWell score does. So,
okay,
because as I said, it might be that you're quite right, Dinesh.
I'm gonna look as well. So I'm not 100% sure.
Yeah.
We will have a look and then probably come back to this.
Yeah. Same here.
And we've got this stratified k-fold, which is using the stratification split into 3, and then doing some training and test, and then all that kind of gubbins. Okay, what was that setting? Has no. Oh, okay. All right. That's just.
So just a question on. Sorry. So just a question on that. If this is this cross-validation piece, if it is actually fine-tuning in here, how do you actually then select the? So we don't seem to do that. We don't seem to say, well, this was the best set of parameters. Let's take that and use it.
Well, as I said, again, we'd have to work out what CrossWell Score does, but I wonder if it's not really meant for that. It's just really a case of, how good is it kind of on different parts of the data, sort of. Because if you only look, I mean, this is sort of saying, I'll train it on some bits of the training set and then test it against some other bit. I guess it just gives you sort of an average of how well it's going to train on that data set.
Yeah, regarding to the previous question, I think, Arsha, you are right, like is splitting the data into smaller sets.
And yeah, so here we've got this using the stratified k-sampling. You've got, so it's splitting using stratified k-folds. Well, again, this is splitting into 3 as well. And then you've got the training index and the test index. And then you're getting X-train folds. And then you've got some test folds. Oh, I wonder if Dinesh was right, and this was what he was saying. And this is the bit where it's got the multiple folds, and it's doing some training folds, some test folds. And then it's doing the training and then checking it against the test fold. And it's all still on the training data. This is not test data. It's still, doing it on the training data and then checking the accuracy for each fold. And then again, there's 3 of those as well. Interestingly, they're both identical. 95.035, the first one, 96.035 for that one. And although I wonder if they're both doing the same thing, but this is just kind of like the coded out version of whatever that guy's doing anyway internally.
So the CrossWell score is automatically doing the stratified folding for you. So that's what he's trying to show, I think. So we don't need to bother about the stratification of our data, how it's dividing, how it's creating a folds. Is it just used whatever is given by the scikit-learn. They have thought through it.
Cool. So, okay, so that makes a little bit more sense. And then what we've got here is the basis. Oh, this is the one where he was saying, you got to be careful with what your distribution is, because it could be that it's purely based on the distribution. You're getting 90% accuracy, even though all it's doing is saying, this is not a 5, because 90% of them are not 5s.
Yeah.
That was a good point. So, and then here we've got CrossWell Predict. Okay. Then we've got a CrossWell Predict. Let's together the two training sets. This is the training prediction. Oh, okay. Oh, this was where he was creating the confusion matrix from the predictions.
So CrossWell Score, that gives you the accuracy of a model, or what are those 96? That's 96%, and 95. That's the accuracy. So the one which we used before is CrossWell Scores, and this is CrossWell Predict.
Yeah. Yeah.
So yeah, scoring is accuracy. Yeah.
And then we've got
CrossWell Predict. This is the confusion matrix.
Okay, so we would. Oops, sorry, I reran that. Never mind.
So the confusion matrix use CrossWell Predict, right?
Mm-hmm.
Yes, yes. So that's only taking the predictions. Yes, yes, we're correct. Yes. And it's interesting. So I guess the you're looking at what's not on the diagonal of the confusion matrix, I guess, because that's all the stuff that's wrong.
Yeah.
Okay, and then we've got, that guy, and then what we got here. Predictions, confusion matrix of, and train perfect predictions. Okay, so this is perfectly predicted because there's only on the diagonal, exactly. And then we've got precision score and recall score from metrics. And that's the precision score. Okay, came out a bit higher this time, 0.837. And that was just a bit of arithmetic there. I don't know why it came out to be different. I haven't changed any of the data. So that's probably going to be wrong. So let's look what the recall score is, 0.65. Because that went high, this went a bit low. And then we've got the F1 score.
So in that case, what he's telling you, if your recall score is high and precision score is low.
So in this case, the precision core score was high and the recall score was low. So and then the F1 score, again, don't really have an intuition, it's 0.73. And then let's look at what are Y scores.
So any intuition on F1 score? What he was saying, do we need the F1 score higher?
Because your F1 is high when both recall and precision are high, right?
And that's what we want.
Yeah, if they're both like, I mean, in theory, they can't really both be, but yeah.
Well, no, he said it depends. This is the one where he used the Safety for Kids video. Where you have to figure out whether that's okay or whether you've got a very sensitive data set and you need to be more careful. So this is the one you need to, it depends on what you need.
Yeah, so it depends upon your on a problem set, but however, we are still trying to pull it up to a 1, even if like whatever the problem of our problem is, obviously few times we may get in the mid 50s, mid 60s, mid 70s based on a problem to problem. However, what we're looking is for every problem we're trying to achieve as high as possible. Is the assumption correct?
But is that even possible because of the precision and recall trade-off?
Yeah, so I understand that. I understand, and that's why we are not going to look into precision and recall separately. we're trying to look as a F1 score.
Yeah.
Now the intuition is like, if you leave the, and I understand the aspect that you will never get to the value 1 because of the trade-off. However, the question is, is my assumption is right that we still like to see higher value with the trying of different algorithms to see if we can get a higher value for F1?
No, I don't think so, because if they're both 50%, the precision is 50% and the recall is 50%, then that will be 1 for F1 because it's just one of the other. Well, actually, it's 2 times, what is the, yeah, there's a formula for it, isn't there? Let me just think. I'm not sure. F1 is precision times recall. So if that's 50% and 50%, that's 25%. 25% is 50 over 100. So that's a half. Yeah, well, yeah, maybe you're right. Maybe trying to make it as high as possible is the best option.
No, in the text just below, it says the F1 score favors classifiers that have similar precision and recall. This is not always what you want. In some contexts, you care mostly about precision. In other contexts, you really care about recall. So that's when he goes into the video example. So it really is dependent on what you're after.
Yeah, and actually after reading this, I would prefer looking at both precision and recall separately and adjust it according to our goal instead of using only one measure, which is the F1 score, because exactly what it explains in the precision recall trade-off. I don't know, what do the others think?
Yeah, no, I think I agree with that. It feels like depends on your data set, but you know, if it doesn't matter to you too much, then you could probably use the score. But,
yeah, like the problem I have is like the data set, like if I am in the mid 50s of F1 or mid 60s, how would I say, oh, I'm doing really, my algo is doing really well? If I don't have anything which I'm aiming for, like in a test in the real world, when I come up with the issue, then I get the F1 score. So what I look up to, what actually I'm trying to find out or achieving for.
Oh, the sentence that I liked, which kind of answers what you're saying, is just above there. It's talking about the precision and the recall separately, and it describes your 5 detector. You know, and it claims an image represents a 5. It is only correct 72.9% of the time. Moreover, it only detects 75.6% of the 5s. And I thought that's a nice way to look at it, because it's telling you exactly, you know, first it's your accuracy, but then overall, how much are you actually detecting, you know? I think using the 2 scores separate, well, for right now, based on very little knowledge, the first, using them separately rather than the F1. But I think maybe it grows with it. Well, it probably grows with experience, right?
Yeah, that's right. Because precision and recall you can understand, whereas harmonic, like, what is it?
Yeah, but interestingly,
favors the both to be similar.
Yeah, I'm like,
I guess
people,
like
I have seen. Sorry.
No, go on.
I have seen people who are experienced. They don't use recall or accuracy quite often. F1 score is kind of like thrown quite a lot as well. F1 score is, isn't it? So interesting.
Yeah. Actually, now that you mention it, in Kaggle competitions, you see that quite a lot, don't you?
Yeah.
Yeah. Okay. Yes.
Yeah, I think we've seen it in Fast AI as well. It's like in the earlier sessions. Not sure.
Yeah, but then, well, I'm reading Wikipedia, one of the most trusted source. and then it is stated that there's a criticism against the F1 score, in which one, it ignores the true negatives, and the other one is that it gives equal importance to precision and recall, which is what we are discussing so far.
Yeah.
So I think, yeah, it will you can always use this, but using the metrics mindfully, I think it would be really, really difficult.
Yeah, but that's, I mean, that's kind of true in general, right? Like I don't think there's any metric that does well in every application.
I think so. Yeah, and also he said that if your data is unbalanced, then F1 score will be bad. But how exactly it will affect that, I'm not sure. So take that with a grain of salt.
Okay.
Cool. And then we've got something about the threshold is 0, and then threshold is 8,000. Okay.
I have to say, the section was not what I thought it was going to be. It's a lot about the metrics and using canned classifiers. And I thought it was going to explain about how the classifiers work. So that was a bit of a surprise. We talked about SVM, and we just sort of blitzed past it. Do we actually cover that in more detail?
Yeah, I think so.
We will.
Okay, right, I see it.
Training, so that was regularization. Yeah, as support vector machines is
Yeah, there's a whole chapter on it.
Okay.
No, next one is training models, and then it's support vector machines. Right. Oh, sorry, is that finished? So that has one. Then this is in plot. Oh, now that is proper bumpy. I don't know what I did to it.
Yeah, this is the bumpy he's talking about.
Yeah, okay. Interesting.
Jeremy also said bumpy.
We've got all, and then we're plotting. This is the precision versus recall. This will be interesting as well. Yeah, so there's some weirdness there because the other one, it was like starting at the top and then going down, where this one was a bit below and then it went up and then kind of went down.
What happened there?
Yeah, so
I'm not quite sure, to be honest. As far as I know, I ran all of them. I mean, and they do set the random seed. So in theory, it should have, there must have been some step maybe which I missed. But which obviously wasn't the most critical thing in the world.
Yeah. Sure.
but I mean, like when we look at the chart, so it looks like the precision keep on increasing as a recall keep on increasing, and that's what we want. Recall increase, precision increase, but then trade-offs start happening, that precision start going down as recall start going up. So
yeah, because I wonder the draft they had in the book, it was just like really right against it. This bit here was
Yeah,
just,
you can see a little dip in figure 3.5 in the book.
yeah, and then we've got the.
But I guess like that's just because like, you know, the bumpiness in the book was also like less than the bumpiness in your image, so it's probably what's making it more pronounced here.
probably, yeah, we didn't put the seed, so it's maybe data shuffled differently when we download it.
Almost likely, yeah. But it's interesting that there were like 70,000 images, so I wouldn't have expected it to be that huge a difference, even if we, you know, well, mind you, I suppose. I mean, there's a lot of data, so it should have been, whatever the overall results were, should have been roughly similar. So 90% precision gives us a threshold of 7,800. And we've got, so that's 90%, 47 recall score. Okay, so now we've gone down to rock curves. So we have a rock curve from the metrics, and then plot rock curve. What is it? So plot rock curve. So this rock curve is doing that. Yeah, I must confess, I don't know what this does. What does rock curve do? Oops.
Plots the false positive rate against the true positive rate for all possible thresholds.
Ah. False positive rate versus true positive. Oh, okay.
Yeah.
So you want as low a false positive rate as possible and as high a true positive rate. Oh, okay, that makes sense that you want it in the top left. Because if it was perfect in the top left, then it would be 0 false positives and all true positives.
Yeah.
Yes. Okay, that makes sense. Yeah. Well, actually, that's quite intuitive then, isn't it? I should have read the axes.
Then they also talk about the arc, which is the area under the curve.
Ah, right. So this is this guy over here,
Which
and I
is,
guess it'll be maximum when the curve is up to there. At one point, the area will be 1, and at the moment, it's always less than 1.
yeah.
Yeah, he mentioned the area should be 1, shouldn't he? Or as close to 1 as possible. Okay, well that's makes sense. And then rock AUC score. So what is a rock AUC score? What is a rock AUC score?
That's your value 1, which you're trying to achieve.
So this is the
It's the area under that curve.
oh, it's the area under that curve, right?
Yes.
Okay. And then we have, now we set number of estimated 100 to be features, and this is the default value in scikit-learn. Okay. Now we've got a random forest classifier, number estimate is 100, random state 42, predict 5, 3. Okay, so this is just a random forest. Are people okay to go on till 8 p.m.? I know it's getting a little bit late.
Yeah, it's good. Well, for me.
So it's interesting. So he's done the full X train, but he's passing it Y train 5. He did explain why he, in the book, but I must confess I've forgotten why he only passed it 5.
I think he's just doing that one-to-many, one-to-all classification.
Yes, Y train's got 60,000 in it. And how many X? Oh, X train has got 60,000 in it as well.
Yeah.
Oh, okay.
Yeah. It's just ones and zeros, and the ones are, the 5s are the ones.
Yeah.
The ones are all zeros, yeah.
Okay, so that's done. And then let's and then we plot that now. Right, so we can see that this classifier, the random forest classifier, is much better than the other one, right? Because the area under the curve is now 99%. Yeah, 0.998. Okay, and then we've got so this is a cross-validation prediction precision. Okay. I can't remember what the state of the art for MNIST is. I'm sure it's about 99.8. Go to the art leaderboard. 99.84. And this is 99.83. Well, mind you, that was the area under the curve. We'll get the actual score from this guy.
Random forest, is that good? Gosh, an MNIST.
Yeah.
That's good.
These are not even neural networks. They're just random forests or simple linear, lots of combinations of linear models. Yeah, 0.99. Yeah, the state of the art is 0.998. Something like that. And the recall score.
That's pretty good.
0.86. Yeah, I'm assuming I'm comparing the right thing as the right thing because it says precision, so I'm not sure whether, well, I'm assuming accuracy means precision. And then we've got multi-class classification. And so this is the support vector machine.
I think accuracy will be like the number of true positives against over like the number of samples, right? So it would just be however many percentage you got correct.
Yeah, well, that is precision because it's true. It's true positive plus false positives. Oh no, it's not totally, is it? So maybe
No,
that's
it's not exactly the same.
quite right because it's missing some of them. Yeah, yeah. So maybe that number is not quite the right thing to compare. So we've done that. So we've done that, and then argmax, some digit scores, and then the classes. The class of file, the string representation of it. And then we've got the one versus rest classifier. And using support vector machines. Okay. Okay. And then length of the estimators, 10. Fit and predict.
So basically the point of this notebook is really to try to get a feel for the measurements.
Yeah, these kind of precision, recall, AUC. I guess it's worth knowing that Scikit has these classifiers. If you have got kind of this kind of slightly simpler, where some of these linear or decision tree models will work for you. But a lot of people would have used a neural network for these kind of problems. So
yeah.
one versus rest. This wasn't that many. There was only 10 of these.
But this is support vector though, isn't it? So it's
Yes.
a little slower, I think.
Yeah, it probably wouldn't have helped to do GPU anyway, because I don't think Scikit does GPU.
No, I don't know.
And then what we've got, so we've got some decision functions. Oh, okay, so the different functions, what the values they're giving back are. So the best one seems to have been that one out of the 10. So I guess while we're waiting for this thing, I think we've gone through most of this. So what do people fancy doing next week? I don't know if there's anything practical people want to think about. We don't have to decide right now. I guess if we decide by Monday or something.
There are like exercises at the back. I'm not sure if anyone wants to go, like, because I think this, it said at the top that the solutions are also in this notebook. So maybe we don't look at them and try it ourselves.
Yeah, that's right. That's right. I think we may look at them.
Yeah, okay. Excellent.
Triangle declare for the honest data that's choose over 90% accuracy on the test. Hint, K plus where works quite well. Oh yeah, I guess so. Yeah, some of these are going to take a little bit of time though. Oh, okay. Yeah,
Well, we could maybe do different ones and just feedback on what we've actually learned.
There is a Kaggle data set apparently that if you wanted to try this code but on something different, there's a Titanic data set.
Yeah.
Yeah.
I think this would be a good idea to work on one of this Kaggle competition, either spam or either there's the one which Titanic you mentioned.
I think some of them the solutions are like below. Yeah, they've got the exercise solutions down there. So if people wanted to check,
Okay.
where was it?
Yeah, but
On that one now. Yeah.
Well, maybe we can pick a data set and then instead of reading for an hour, perhaps we can try to work ourselves for a certain amount of time, and then afterwards reconvene and then exchange notes about how we approach the data, what's the accuracy or whatever metric that you use from the data. I mean, the book is called Hands-on Machine Learning, right? Without any hands-on practice. I think it really defeats the purpose of the book.
Yeah. Okay.
So why not among the exercises, like we can pick one, like the Kaggle one. Yeah.
I mean, trying out all the 3 data sets, I guess it would be too much.
Yeah, sure.
Yeah, exactly. No, that's cool. I'm
Yeah,
happy with
sounds
that.
like a good idea.
Yeah, why not to go with the Kaggle? Wow, perfect score.
Yeah.
I think with some people they knew what the answer was, so they were able to use that, I think, to generate.
But nowadays, like the data set has been for a while, so people have been trying out. So it's pretty straight, I think. I think we may try this data set and discuss how we approach. I don't know.
Yeah. Okay.
Yeah, well, I think working on Kaggle is definitely a good idea.
Yeah, sure.
That's definitely, we're going to end up maybe a 3 months, 6 months time. So why not now?
I agree. I mean, you will only learn after you're getting your hands dirty, right?
Yeah, absolutely. Yeah.
It's
just pointless memorizing all these codes.
It is. I'm like, even I have gone through lots of these pre-built Jupyter notebooks. You just press enter, 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 enter. But when it comes for you to write a code, you just lost. You say, oh, what do I write? You have no clue. So definitely writing your own code and then learning by doing is, as you said, it's hands-on. So let's get into hands-on.
And if we work on the same data set, then at least we can compare notes. You know?
Sure. That's right.
Okay, cool. I'm up for that. All right.
So it's the which Titanic is the data set we are working, yeah?
Yeah, so I guess if you look at this Titanic one, I'll put it in the chat.
Cool. Okay.
Where's the chat gone? I'll try to find where my blue chat is. There we go, here's chat.
You can see how many different ways you can get a score of 1. Look at our orcs and our rocks and our F1s and our whatnots.
What's wrong with this code? It's running for a while. Does it need a GPU?
One for all, so there's only 10 of them, but I guess it is 10 support vector machines that are being run, and then some of these, it's really easy to run like loads and loads of things in the background, even though it's just one function. Yeah, also, we don't know what kind of machine Colab has given us. It's probably some fairly low-powered thing. Can't imagine they'll be generous and give us anything good.
Oh, yeah. I don't know if anyone knows like how to keep Google Colab on. If I like for a while, 10 to a minute, I didn't touch the Colab, it just disconnect, and I need to is there any way like I can keep it running at the background?
Yeah, I think if you Google it, there is a small, what you could do is there is a software which you need to download, which kind of like not let your screen go off.
Okay.
I think I tried once and it worked. So it keep refreshing your screen, which simulate that you are working on it, and then it won't go off.
Nice.
I thought you actually had to run cells in order for it to stay on, because sometimes even when you're just looking at it, it does disconnect.
Yeah.
Yeah, but then I'm talking about if you're running, if your program is running.
Yeah.
Yeah, okay.
In a sense, like when you're training, and then the training takes hour or two to run. But if you switch off, like if your screen locks, you get disconnected, even if your program is running. So
what we do, or what we have done, is we always have like a model save or learn.save or whatever, save a checkpoint after that. So in the same cell. So when you run the cell, if you happen to miss it for some reason, it does actually save its state. You can come back to it later.
Yeah, in fast AI, right?
So that might be useful.
Okay. Okay. Thank you.
Yeah, cool.
Just kidding. I probably shouldn't have pressed enter. It's almost 8 o'clock. I'll probably close it in a minute. Yeah, so there's some interesting stuff in there. Not something I'd come across, being more neural network based. Yeah, cool. So so people think have a look at this Titanic and pick. Well, I don't know. I mean, because there were a few different things we could have done here, wasn't there? There was these either using just stochastic descent or decision trees or random forests. I don't know if people want to just choose something they want to play with and maybe do a few of these plots. So this Sunday, I don't know, do you guys want to have the day off because all the US guys are having it off?
Oh, the US guys, I don't know.
Or do you want to work on this Kaggle thing?
Anyone from US here?
No.
No, it's quite. What is it? It's probably about lunchtime for them, so they're all probably at work.
I guess we can meet. We can convey on Sunday.
We don't have to decide now. So I think a lot of us are on the Saturday probably. Oh, I don't know actually. Is it even the Saturday one? Because Saturday is
both days off, I guess.
Yeah, yeah. So you know, we'll decide maybe say on Sunday lunchtime. I'll put a message on here saying, do people want to, are people still free? Do they want to do it? If so, I mean, I'm working anyway. I've got my own pet things that I'm working on, so I'll still be around. And yeah, and this meeting should be persistent now. We can start it whenever we want and keep it going.
Cool. Yeah, I'm easy. I'll be working on the weekend, so.
Cool. I guess as a PhD student, you never get any time off.
No.
Yeah.
You always feel like you have to work more. So.
Are you actually writing yours up at the moment, or you still have some stuff to publish and stuff? Because I don't know how it works with the AI.
I'm still trying to publish something. So hopefully this year something else will come out. So my second paper, hopefully.
Cool. So have a nice weekend, guys, if I don't speak to you on Sunday. But yeah, let's hope to see if we connect on Sunday and maybe see Or we could even just, because we've got like an hour and a half, let's just have a little look at it, download the data, and then each of us can start playing with it. So my assumption is that we haven't probably had a chance to look at it until then, and we'll all kind of go away and say, well, for about an hour, see how far we get, come back,
right.
and then we can then pick it up on Wednesday, I guess, and then, you know, see where we can get on there, whatever we were doing on Sunday.
Okay. Sounds good.
Cool. All right.
Cool.
Okay, cool. Speak to you on Sunday.
Thank you.
Bye.